Greetings everyone, this is Mr. Mull. Today I'm doing a podcast going over some of the fine-tuning needed to do the light work homework. So I'm going to talk about waves a little bit and how to use those equations for waves in order to solve for some unknowns. So we're going to go ahead and get started. Okay, so the first thing we need to worry about is, well, what is a wave? A wave is a flow of energy through some type of medium. So energy is being transferred to some type of medium. It could be water, it could be earth, like in an earthquake, it could be through the air in the form of a sound wave, or it could be a wave of light. Energy is being transferred through a medium. Okay, so this is what a wave is. So we're going to talk about some properties between different variables associated with waves. Wavelength and frequency. So if I'm drawing a wave here, and I have a wave, and I want to change the wavelength of that wave. Okay, so I'm going to draw another wave, and let's say the wavelength goes down. Okay, so wavelength goes down. That means the peak to a peak, the distance from a peak to a peak, actually is shrinking. So let's say it was 8 centimeters, and now it's only 4. So if the wavelength decreases, then the frequency of that wave, or the number of cycles of that wave in the same amount of time, goes up. So if this goes down, this goes up, and vice versa. So if one goes down, the other goes up, they are responding inversely. Okay, so this is an inverse relationship. Now, mathematically, it turns out inverse relationships, these values are going to, when they're multiplied together, always equal some constant value, the speed that the object is traveling. So if my wavelength goes down, my frequency has to go up to make up for it, so we can still have them equal to the same number. So, for light waves, these two things, when multiplied together, equal c, the speed of light in a vacuum. 3.0 times 10 to the 8th meters per second. Okay, it's a well-documented constant. So there's this inverse relationship. Energy and frequency. If I add more energy, so let's say I turn on the water faucet, we have a lot more energy. Waves are going to get busier. Okay, there's going to be a lot more going on. So if I turn on the water faucet more, we're going to have more energy, my frequency goes up. More energy, frequency increases. There's also a mathematical relationship here between energy and frequency. When I take energy and I divide it by my frequency, those are always going to equal some constant value. And Max Planck, is the scientist who came up with this value, and we call that h, and I'll give you the value for that in a second. So these are related. If energy goes up, frequency has to also go up. You know, if I have 10 joules of energy and my frequency is 10 hertz, that would equal some constant. If energy goes up to 100, well, to be equal to the same number, so does frequency. They both have to go up. So this is going to be directly related. One I wanted to talk about was amplitude and wavelength or frequency. Remember, amplitude is basically the height of our wave from the medium, from the baseline medium. So our wavelength, our amplitude was here. It turns out that the amplitude is not affected by frequency or wavelength. Okay, so there's no effect. Amplitude really deals with the intensity of the wave, so such as brightness, how bright is our light wave, brightness, and we're talking about sound waves, the loudness. So we're talking about intensity. Okay, so what we need to do is we need to learn how to use these relationships. So these equations we're going to use. I want to I want you to take note of a couple things. In my equation here, I'm going to draw a little square around my C and my H. These two equations each have different constants involved that relates the two variables mentioned. So c is going to be the speed of light, 3 times 10 to the 10th centimeters per second, or 3 times 10 to the 8th meters per second. And then h is Planck's constant, which is 6.63 times 10 to the negative 34th joules times seconds, not joules per second. I also want you to note in these equations that frequency is in both of them. So if you wanted to, find wavelength and you only knew the energy, you're going to have to first find the frequency. Okay, frequency could be a middleman. If I know wavelength and I wanted to get to energy, I might have to go through frequency. Okay, so frequency is something that these equations share in common. So I'm going to take just a moment and I'm going to do a couple problems from the homework, and hopefully this will be helpful for you. Okay, so this is questions 1 and 3 from the light work homework. I have the equations up here. And what I like to do is I like to manipulate my equation and mess with the letters first and then plug in numbers later. Okay, so let me show you what I mean. Let's look at the first problem. I have energy. They give me 7.50 joules. Now, joules is just a unit of energy. Which equation should we automatically rule out as I'm doing my first calculation? Looking at my 2, can I automatically rule out this one here, at least for right now, because I have energy. So I'm going to need to use this one first. And maybe we'll use that second one in a second. But we're definitely going to use this equation. So I can find, using this equation, using the energy, I can find the frequency. Remember that h is that constant. That's not going to change. So I'm going to go over to frequency. E equals hf is my original equation. I like to mess with the equation first. So I'm going to solve for f. So I'm going to divide both sides by h. And rewrite that. Frequency is equal to energy over Planck's constant. Now that I have an equation for frequency, I can go ahead and plug those values in. So I'm going to go ahead and find my frequency is equal to energy is given. I'm going to leave my units on there as I'm showing my work. 7.5 joules divided by h is Planck's constant. So I'm going to look over and I'm going to punch that in. 6.63 times 10 to the negative 34th joules times seconds. Okay, I can just put a J there. And so looking at my units, joules on top, joules on bottom, and I can divide this out in my calculator. Careful with that negative exponent. You're using that E function, that times 10 to the on your calculator. So I punch all this in. The unit left standing is nothing over seconds, but that's okay because isn't frequency's unit cycles per second, something per second that's happening? So it's okay that the unit's on the bottom. That's true. Okay, so frequency is equal to, and for number 1, you'll get an answer of 1.13 times 10 to the 34th hertz. Okay, hertz, remember, is cycles per second. So because I have nothing on top and seconds on the bottom, it's going to tell me it's a unit of hertz. Okay, so we've got this one. Circle my answer. We're going to go ahead and take a look at the next one here, find the wavelength. So looking at my equations, well, to find wavelength, I'm going to have to use this one that I originally erased. So I'm going to go ahead and give me 1 second. We're going to go back there from current slide. Okay, so we're just going to leave that up there. But we're going to go ahead and use that equation. So I need to solve for frequency. So I'm going to take my original equation, C equals wavelength times frequency. I'm going to rearrange it to solve for wavelength, lambda. So I divide both sides by f. F's cancel. My wavelength is equal to speed of light over the frequency. So now I can plug stuff into my equation that I've manipulated and go from there. So I'm going to go ahead and do that. Wavelength is equal to speed of light. I look at my constant value up here, 3.00 times 10 to the 10th centimeters per second. And I'm going to divide that by my frequency. So my frequency, we solved it. It was 1.13. 1.13 times 10 to the 34th hertz. Or the unit for hertz is per second. I'm doing that so I can show you the units canceling. So I have per seconds on top and per seconds on bottom. Same thing on top and bottom, they cancel, leaving me with the unit of centimeters, which is a unit of length, which is okay for my wavelength. So I punch that in, and I'm going to get an answer of 2.65 times 10 to the negative 24th centimeters. Now I'm going to warn you, it's okay that you're going to get really small wavelengths because light is a really, really small wave. So you're going to get really small wavelengths and really fast frequencies because those light wavelengths occur a lot of times per second and they have very small wavelengths, so expect those numbers. This spectral region thing over here, we're going to talk about that when you return, and I hope that this video was helpful.